let's talk about integrated rate law equations. So integrated rate laws are looking at a kinetic expression where we have 2 points of data, and we're going to essentially either find out the time it took to get between those 2 points, or given a time, seeing how much has decayed over a given time. If the two most common ones are first order and second order. While there is a zero order, it is less commonly used. But the first order one is prevalent, especially when it comes to nuclear chemistry, because all nuclear chemistry is all nuclear chemical reactions are first order reactions. So if you know how to do first order, you know how to do all nuclear chemistry. Rearranging this to talk about the half-life, we can find the half-life equation is ln2 equals over T1 half equals K. The second order one is 1 over A equals KT plus 1 over A0. With the half-life being what, like it's like the half-life being like 1 over A0 T1 half. I'd like to say K, something like that. Something like that. But so how do we do it? If we have like a first order reaction, say first order, we'll say a half-life of 800 seconds. And I want to know how much is left. What's A after 100 grams is allowed to go react for 20 minutes. Hypothetically, how much is our A concentration after 100 grams reacts for 20 minutes? So in this case, I'm not giving you the K. You have to find the K with a half-life. In this case, you say, well, ln2 over 800 seconds would give us our K. ln2 divided by 800 would be a K of 0.000866434. Okay. Now, we have to turn our 20 minutes into seconds because this is units of 1 over S. So if I multiplied this by 20, I would not get the right number. So 20 times 60 is going to be 1,200 seconds. So with that in mind, plugging that in here, we're saying ln of A is equal to negative 0.000866434 times 1,200 plus ln of 100. 0.0866434 plus ln of 100. Okay. So that's going to give us ln A is equal to 3.565. The last step is to make sure you find out what is A, not what is ln A, but what is A. So to get rid of ln, we take the inverse log to both sides. The inverse log. So how much is left? 35 grams. 35.36 grams. Does that make sense? Well, half-life is 800. So 2 half-lives would be 1,600. We have allowed 1,200 seconds to pass. 1200. So it's somewhere between 1 half-life, which is 50, and 2 half-lives, which is 25. Is 35 between 50 and 25? Yes. So does 35 seem like a reasonable answer? Yes. So for example, if you don't know how to set this up, you don't know how to get the correct answer, but you know, like, you're given a half-life of 800 and 1200, you know your answer has to be between 50 and 25, if you can reason that part out. Do a second order integrated rate law. We're going to say K, well, I'm going to simplify, and K is 0.835. 1 over S. And I say, how long would it take to go from A sub 0 to how long would it take to go from 100 grams to 10 grams under these situations? How long would it take for that? Our second order equation is 1 over A equals KT plus 1 over A sub 0. So plugging in what we have, 1 over 10 equals 0.835 T plus 1 over 100. So first thing is I will get the 1 over A sub T to the other side, A sub 0 to the other side. So I'd subtract both sides by 1 over 100. So I'd have 0.09 equals 0.835 T. And then I divide by 0.835, and I would get the time would be incredibly short, 0.1078 seconds. But that is because K is actually a pretty big number, I guess, in this hypothetical situation. So 107 milliseconds would be the answer. But those are examples of integrated rate law equations in action.